epithelium and connective tissue form the integument. A haiku to live by. Today we are going to start talking about, two of the four major tissue types. Yes?
Oh, I was just confused by one of the questions on the back, just before we get started. The
Sure.
one where the patient had low parathyroid hormone and high calcium.
Mm-hmm.
So
If
is
he
that
has
like a decompensation response, or because you would think that if they weren't unable to produce parathyroid, they wouldn't be able to bring their calcium up.
if they were not, so they have low, okay. The choices, if you have high calcium, are going to be either hypercalcemia with malignancy. You have some sort of cancer that's elevating your calcium levels, or you have. I'm not sure if I'm fully understanding your question, or you're going to have hyperparathyroidism. Okay, one of those two. The other two options were renal failure and hypoparathyroidism, but those both have low calcium levels. So with the two options that had high calcium, either cancer, which is going to liberate a bunch of calcium, or the hyperparathyroidism, we have the follow-up finding of low parathyroid hormone, so that you are drawn to the conclusion that this person must have cancer. They have hypercalcemia due to cancer. Okay, and with looking at those choices, you see that you have extraordinarily high calcium. So the one of those there that indicates that would be hypercalcemia, right? And then and without having to remember the diagram. And then I say that there's low PTH. Well, that's going to be hypoparathyroidism. Or low PTH would be distinguished by not being hyperparathyroidism of those two options. Right? Does that make sense?
Okay.
So now say your question again, because I'm not sure if I followed it, actually.
So I guess the reason, so they have both those findings, but the reason they have high calcium is not because they have low parathyroid hormone. It's because they have
cancer. Mm-hmm.
Okay.
Does that satisfy your curiosity?
That satisfies my curiosity.
Okay.
I was just wondering if I had gotten my...
No. It was a tricky question. The wording was a little convoluted. I have to have something so that everybody doesn't get all the points, just to spread it out a little bit. All right, here we go. Well, in each of us, there are 50 trillion cells. 50 trillion cells. There's only 8 billion people on Earth, and we have a hard time living together. We have a hard time living together, just the 1.3 million people in the state of Maine. There are 50 trillion cells in your body that are all working together. Of those 50 trillion, there are approximately 200 different cell types. That's pretty astounding. That's astounding to me, at least. Each of these different 200 types of cells is roughly categorized into 4 different broad categories of tissues. What, you may ask, is a tissue? Well, it's a collection of cells and cell products that perform specific limited functions. There's a very discrete definition for you. Tissues then come together and form organs. So an organ is some kind of structure that has discrete boundaries and is made up of multiple tissue types, okay, of multiple tissues. There are 4 primary tissue categories. Primary tissue categories. We're going to speak of 2 of them today. We're going to cover half of all the tissue types, well, not just today, in the next 2 or 3 lectures here. And these are epithelial tissue and connective tissue. So epithelium covers exposed surfaces. It's going to line the passageways of glands, and epithelia are going to have a polarity to them, as we shall see in subsequent slides here. Much of that is probably going to be a review for some of you. Then there's connective tissue. Connective tissue is probably the most diverse category of tissues. There's many different connective tissue types. We're going to go through a survey of them. These fill in the spaces. Connective tissue, as the name would have you believe, is sort of the glue of the body, oftentimes. Connective tissue is going to form the fascia. It's going to support other structures in the body. It's going to be responsible for transporting material. So blood cells are considered to be part of the connective tissue category. All right, and then adipose tissue, which is connective tissue, is responsible for storing energy in the form of fat. The other two tissue types are neural and muscle tissue, and these two tissue types have a lot of similarities. They're both excitable tissues. Neural tissue is going to carry electrical signal for the nervous system from one part of the body to the other. And then muscle tissue is contractile tissue, of course. Also excitable tissue. We'll talk about the membrane dynamics that give rise to the function of those two tissues in subsequent units here. But before we get to those, today is all about epithelium and connective tissue, two tissue types that work together closely. And what I've done here is outlined. This is a broad outline of everything I want to talk about in this unit. And so this is the sort of thing. I put this up here not only to give you a sense of what we're going to talk about, but also a sense of what a rough outline of your notes might look like as you're going through. You guys have gotten here, presumably you all know how to take notes and do outlines. But you'll notice there's not a lot of detail in here in this outline. That's the kind of thing that you want. You want a rough outline so that when you come to class with this outline, you can fill in the details that I talk about and emphasize in class. Okay? So we're going to talk about epithelia and glandular epithelia. These are the two broad categories of epithelium. Then we're going to move on to connective tissue, and that is distinguished between dense and loose connective tissue. There's 9 types of connective tissue proper, and then there's going to be fluid connective tissue and the supportive connective tissue. Finally, muscle tissue and neural tissue are for other units. We'll talk about those in other units, but I will talk about membrane types, the 4 tissue membrane types. And tissue membrane types come from the interaction of epithelia and connective tissue. All right, mucous, serous, synovial, and then finally cutaneous. And I'll put quite a bit of time at the end of the unit into talking about the cutaneous membrane or the integumentary system, right, your skin. Good? All right. So for those of you who go on to medical school, I hope that your embryology class is as interesting to you as it was to me when I took it. It certainly gives you a much deeper insight into the design, maybe design is a loaded word, the organization of the human body. Here, embryologically, there are 3 germinative layers, and they're color-coded and depicted in this diagram up here. Each of these germinative tissue layers, specifically named the ectoderm, the mesoderm, and the endoderm, these tissue layers give rise to discrete structures in the body, discrete organ systems. The connective tissue and the epithelium are throughout these 3 categories. Okay, so the epithelium does not specifically derive exclusively from mesoderm or ectoderm, but the ectoderm does give rise to the epidermis, the outer layer of skin, the very outer layer of your skin, and then the nervous system. The mesoderm well, let's go to the endoderm first. This is the inside. We are you can think of one way of thinking of humans is as a giant feeding tube, the coelomic cavity. This is lined with a mucous membrane, both in the digestive and respiratory tracts. Endoderm gives rise to a whole host of digestive organs, such as the liver and pancreas, etc. And then the thyroid gland. Tonsils are also endodermally derived, which is interesting and notable because all the other lymphatic tissue is derived from mesoderm. The mesoderm gives rise to the mesentery, mesenchymal cells, muscle cells, skeletal cells, cardiovascular system. The dermis, so there's the outer epidermal layer of the skin, then the deeper layer of the skin is called the dermis, and that is mesodermally derived, and also the urogenital and reproductive tracts come from mesoderm. All right, so first to look at a generalized schematic of an epithelial cell. There's two categories of ET. This is epithelial cells proper, and then glandular epithelia. So epithelial cells cover surfaces, and even in glands, they're covering a surface. They're lining the lumen of whatever glandular structure we're talking about. Glandular epithelia are going to produce secretions. Okay, so the characteristics of an epithelial cell hopefully are familiar to at least those of you who've had any kind of basic cell physiology before. There's going to be a cellularity to them. That means there's going to be, and this is a very obvious, characteristic. They're going to have junctions with one another. All right, and we'll talk about the significance of that in a bit. Epithelial cells have a polarity to them, and this also may seem like a very basic characteristic, simplistic characteristic, but from a molecular standpoint, it's still not entirely a resolved issue as to how that polarity arises. I remember being in graduate school, and this was a very active area of research as to how an embryologic stem cell that does not have a polarity or a directionality to it establishes that directionality and then developmentally and functionally adheres to that. So this polarity gives rise to an apical and a basolateral surface. You can think of it as top and bottom, but that's not really true. That's just the way we draw it. Apical is the surface typically across which there's being some sort of secretion, or if it's a proper epithelial covering, that is the layer of the cell, the face of the cell, that is open to whatever lumen or outside compartment or outside world that we may be talking about. All right. So there's the apical surface, which is the exposed surface of the cell. There's the basolateral surface, which is usually in contact with another cell type, connective tissue typically, or if it is a stratified epithelium, it'll be laying on top of another epithelial cell. But the basolateral surface is connected to some other cell, the connective tissue in this depiction. So at the basolateral surface, it is connected to this basement membrane. So there's a connection via the basement membrane of the basolateral surface to this connective tissue. Epithelial cell layers are avascular, and this is a consequence of their cellularity, and we'll see what that means in coming slides here. But there are going to be no blood vessels penetrating up between epithelial cells. It's avascular. So they're getting their nutrients by diffusion, tissue diffusion. Epithelial cells are able to regenerate themselves. They are mitotic cells. What do? So they can afford physical protection. They're going to control the permeability. So the cells lining the intestinal lumen, for example, are going to control what is and is not being absorbed from the intestinal contents. Okay, they're going to control the permeability across a barrier. They form a barrier, and they're going to control what gets in and gets out. Oftentimes, they can be specialized to provide sensory information. They can interact with the nervous system, and we'll see some examples as the semester progresses of this. And then glandular epithelium are going to make special secretions, and that often happens in the Golgi apparatus, the ER and the Golgi apparatus, and we form these vesicles, and the vesicles fuse with the apical surface, that plasma membrane of the apical surface, and release those contents in terms of secretions. There's multiple ways of having secretion. That's not the only way. Exocytosis is not the only way. We're going to talk about 3 distinct ways of secretion later on in this unit. Okay. So the cellularity, these intercellular connections. Perhaps you've talked about this stuff in some of your other classes. We're not going to get into it super deeply on the molecular level, but we do have these sort of cartoons here. There are 4 types of protein constructs that lead to connections, intercellular connections. The first of them is this tight junction. The tight junction, you can imagine the tight junction being like a zipper or like a Velcro, a zipper that zips along the entire apical surface of the cell, connecting it to the adjacent cells, the adjacent apical surfaces. So nothing can get through these tight junctions. There's a host of proteins. This is not a single protein. It's a protein complex. Yes, sir.
Sorry, I was under the conception that the apical surface was like facing towards the lumen.
Mm-hmm.
But is it also facing towards the other cells to the side? Is that called?
No. No. So let me see if I can draw a picture for you here. We'll just have a cell, and it's going down here. All right. So this is the apical surface. Here is some other cell, and here is some other cell. All right, and there. Whatever, and along the edges where these apical surfaces meet, this is where we're going to have the tight junctions, right in here, okay?
Okay, so on the edge between the lateral and
between the lateral and the apical surface is where we're going to have the formation of these tight junctions. And there are these successive rows of, and actually Velcro is a pretty good analogy because it does, on the microscopic level, this is actually what Velcro kind of looks like. There are these tight interlocking protein constructs. And then below that there is a reinforcing adhesion belt. This adhesion belt ties in to this web of intermediate filaments, actin filaments that form this structural web that underlays the apical surface of that cell and is able to relay torsional and shear stress into the tensegrity of the cell itself. Okay, and so we'll save gap junctions for last. The next is these two here, desmosomes and hemidesmosomes. Desmosomes are like spot welds. Did anybody take shop class in high school? It's probably gone out of the curriculum, but I took shop class in high school, and you take two pieces of sheet metal and you stick them, you just lay them on top of one another, and you stick them in between this thing, and these two fingers come down and go zzz, put a big current through there and weld the two sheets of metal together just at that spot, okay? And that's what I think about when I think about a desmosome. They're just these little spot welds along the lateral surfaces of these epithelial cells, and they keep so we're adhered along the tight junction, but they keep the rest of the cells from getting twisted or shifting too much with respect to one another. Okay, these desmosomes. A hemidesmosome is the same thing, except it's hemi. It's only half, right? In a normal desmosome, you have complementary structures coming from either cell. Again, interacting with the intermediate filament cytoskeleton of the cell there that is translating information into the overall structural tensegrity of the cell, right? So there's these filaments going out into the body of the cell, and the two cells are adhered in a desmosome. In a hemidesmosome, we have that same structure, but then it is interacting with different proteins as they reach down into the connective tissue matrix that forms the basement membrane. Finally, gap junctions. Are there any sailors out there? Anybody likes to sail in a boat? So you have a sheet, and it has its the grommets that are put in the sheet. That's exactly what a gap junction is. All right, they're just clusters of grommets. They're clusters of grommets that provide a passage for small solutes from one cell to the next. This allows syncytium, or the confluence of cytoplasm between adjacent cells in an epithelial layer that have these gap junctions are syncytial. All right, and we'll see this isn't just in epithelial cells. For example, cardiac muscle cells also use these gap junctions, and you'll find them throughout neural tissue as well. In fact, in neural tissue, they are responsible for some very interesting behavior in a neuron, but that's for another day, probably another class, maybe another lifetime. All right. Are there any questions on this? Yes, sir.
Oh, so those filaments, those red filaments that are in the adhesion belt and also in the hemidesmosome, those are part of the cytoskeleton?
Yes, absolutely.
Okay.
Yep. Yeah, so there is this complex web of cytoskeletal elements that, and there's this general notion of tensegrity. So the structural dynamics of a cell, that one part of a cell is responsive to what's happening structurally, physically in another part of the cell, and that information is being conveyed in a biophysical sense through these intermediate filaments that are connected at the hemidesmosomes, desmosomes, the adhesion belt. All right. So epithelia is broadly categorized as such, and this is almost more anatomy. This is microscopic anatomy, but I'll go through it quickly. There are simple and stratified layers of epithelium, and you can appreciate what that means. A simple layer means there's just one layer of epithelium before you hit the connective tissue. Okay? Simple and stratified. Stratified has strata, or layers. Okay? And then across those two categories, we have these three morphological distinctions. We have squamous. Squamous. Squamous just means squished. When you get into an anatomy class, you'll talk about the temporal bone, the bone right up here at your temples, called the temporal bone because it shows the passage of time. This is where your hair goes gray first. And the temporal bone has a part of it right here beneath this muscle, the temporalis muscle, that's called the squamous part of the temporal bone. Squamous because it's super thin. You can see light through it, right? Squamous just means squished down, flattened. Cuboidal is very descriptive, as is columnar. Now, there are these two other categories here. There's pseudostratified columnar. Pseudostratified, pseudo meaning false. It looks stratified, but it is not. It is a simple tissue layer. It looks pseudostratified, but it's because the columns sort of do this. And on any tissue section, you're going to see this. It looks pseudostratified, but it's not a true stratified epithelium. And then this transitional epithelium here in terms of stratified, you find this in the lumen of the bladder, the urinary bladder. It's extremely stretchable, extremely stretchable. All right. Glandular epithelium. So there's two categories here. There's endocrine glands and exocrine glands. And nary the twain shall meet. Endocrine glands release hormones. They release hormones into the interstitium. There are no ducts. They're releasing their hormone directly into the interstitium, and whereby it's able to pass into the bloodstream. These are endocrine glands. Epithelia, but glandular epithelia, but they do not form ducts. On the other hand, there we have exocrine glands. Exocrine glands. These produce secretions through ducts onto the epithelial surface. So endo, inside, secreting something inside, into the fluid compartment of the body. Exocrine, producing secretions into some sort of luminal space, not within the fluid compartment of the body. Does that make sense? Confusing? No? Good. These endocrine glands, there are three different modes: merocrine, apocrine, and holocrine. We'll give you examples in another slide here. Just some definitions. A secretion is a useful product to the body. That is something the body is secreting. It is keeping for itself. If you were to secrete, you get home and you smell cookies, you run into the kitchen, you grab as many as you can in the folds of your sweater, and you run off. You have secreted those cookies to your and this is I'm thinking of my daughter actually, but you bring them back to your bedroom. You have secreted them secretly. Excretion is a waste product that you are getting rid of. Okay. So merocrine secretion. These secretions are produced in the Golgi, and the secretions are released by vesicles via the process of exocytosis. So an example of this would be sweat glands. And what is the purpose of a sweat gland? This is a loaded question because there's more than one type of sweat gland. But yes, Jacob.
So in earwax, type of sweat.
That's a ceruminous gland. It's a ceruminous gland.
Okay. Then not earwax. But
just sweat. Just sweat. Give me sweat. You're running. So
okay,
what?
Sorry,
Okay.
I'm overcomplicating things. It can cool you down. That's
There you go. Thank you. Yes. The goal is to produce fluid. and to release as much fluid that's going to evaporate as possible. All right, that's the primary goal of what's called sensible perspiration. We're not trying to, there's no other objective here. Apocrine secretion, also produced in the Golgi. What happens here is instead of releasing vesicles, the cell sheds part of its apical surface. It pinches off and sheds part of the apical surface of that cell. So an example of apocrine secretion is a mammary gland. Why would a mammary gland want this kind of secretion? Instead, we're making milk here. Why not just mammary, just pump out as much fluid as possible? Yeah, Jacob, what do you think?
Because it takes a lot of energy to get that fluid out of the cell, so maybe it takes less energy. You can make a lot faster this way.
Okay, so we can do a large volume at once. What else? What do we know? Does anybody know? Yeah, no.
Does that do like mammary glands, like the bruised milk, they have like certain proteins and nutrients, so it comes out of the cytoplasm contains those.
Yeah, so in milk, it's not just, what do we know about milk? What happens when you take pure raw milk? What is that stuff like? Has anyone had raw milk before, a cow's milk? Yeah, what is that stuff like?
It's very bitter.
It's a little bit bitter. What else? What does your mouth feel like after you drank it? Let me think of it now.
You kind of have like this solid. It kind of sticks to you.
It kind of sticks to your mouth. Not everything in milk is water soluble. It's fatty, right? There's a lot of non-water soluble things in milk. It's a very fatty liquid. It's a fatty liquid. Well, how are we going to get these fatty lipids and hydrophobic proteins to exist in this aqueous solution? We're going to pinch off a whole bunch of membrane, all right, into which are inserted the lipids that we're interested in, into which are inserted the lipophilic proteins that we are interested in. The membrane itself is part of the nutrient content of the milk. Okay? Apocrine secretion. And then finally, holocrine secretion. So this holocrine secretion happens by cells just blowing themselves up. They just blow themselves up. Typically in a stratified epithelium. Cells just blow themselves up on the surface of that epithelial layer. And they're replaced from below by mitotic glandular stem cells. So an example of this is a sebaceous gland, the ceruminous glands that Mr. Laser was talking about. What is a sebaceous gland? Anyone know what that is? Sebaceous means skin oil. It's a gland that makes oil for your skin. What's the purpose of skin oil? It's not to sell clear cell. What? Yeah.
Part of it would probably be like for its hydrophobic properties.
Yeah. And so it's providing a water impermeable protective layer on the skin. It's preventing dehydration. Yeah.
I was going to say, so we're not like something like a reptile. We don't have scales to hard surface to keep the water inside our skin, so we need something to keep it supple and hydrated so it can keep water out but then also not crack.
And keep water in as well.
I didn't mean
Both.
Keep water out.
Yeah, yeah,
water
keep-
in, 'cause, well, yes, also keep water out, but I was thinking just keep your liquid inside you.
Yeah. So what happens here, when these cells burst, all of the lipophilic contents, including all of the membranes in those cells, forms that can form, are part of that secretory output. They can form the sebum or the cerumen, the earwax that is produced by the ceruminous glands in the ear. And so they use all of the contents of the cell to do that. Holocrine secretion, yeah.
Would that be through necrosis or is it more apoptosis?
It's apoptosis, yeah. They go through an apoptite. They become quiescent as they move up the layers of the strata and then go through apoptosis and blow apart. Yeah. Yeah.
When they're like, are they similar in other cells where they kind of package up
In algal cells?
to other cells
Oh.
where they're like packaged into apoptotic blobs, or is it more like diversified?
Packaged into apoptotic blobs. No, it's just that it's that surface layer as they're going up. It's a process. It's a cellular process that starts here and then terminates as they're getting pushed up from below. As they reach the top, they have reached the terminus of that cycle, which results in their destruction. Yeah.
And these three methods are what's also used by the glands with lumens that secrete things inside the body as well, like things that secrete into your intestinal tract or into your lungs or something like that.
Yep. Any glandular epithelium is going to be one of these three. All right. This is more anatomy than we need. I don't want to go through all this. There's all kinds of structural classifications. This is not physiologically super relevant to our discussion. I should have taken these slides out. I apologize. Okay, on to connective tissue. So, three broad categories of CT. We said there were two categories of epithelium. What were those? What were the two categories of epithelium? Glandular and then just regular epithelial cells. Okay? But now there are three categories of connective tissue. We have connective tissue proper, fluid connective tissue, and supportive connective tissue. And this will be the last slide I talk about. I'm not going to go through it in amazing detail now. This is a preview for Friday. So on Friday, I'm going to go through, in the connective tissue proper, there's two subcategories. There's dense and loose connective tissue. And within each of those, there's three categories. And we'll talk about each of those and give some examples of each of those. Across these two categories, these 6 types, there are going to be 9 cell types of connective tissue proper that are going to combine in various ways to give us these different connective tissues. Then the second category of connective tissue is fluid connective tissue. And this is your erythrocytes, your leukocytes, and whatever interstitial fluid and lymph that you may have. Okay. Finally is the supportive connective tissues, and there's 2 categories of those, cartilage and bone. Okay, so finally, these are the different functions that you can find in connective tissue. They help bind organs together. Support is obviously the bone and cartilage. Heat production, storage, transport, blood. Yeah, we're going to go through each of these in turn when we get to the cell types or tissue types that correspond to those. Are there any questions? Okay, good. Just slow work of grinding through the material. Good work, guys. Thank you very much. A lot of material here.